So 3I Atlas has recently passed its closest point to Earth, and today we receive some major updates about its true size. What's surprising is that these new calculations completely contradict the measurements scientists have been reporting for months. On December 23rd, researchers released fresh calculations estimating how large 3I Atlas actually is. This time they determined its size by analyzing what's known as non-gravitational acceleration, a very small push caused when gas escapes from the surface of the object, creating a rocket-like effect. Scientists measured this non-gravitational acceleration at 89.3 kengs, 9 astronomical units per day squared. In simple terms, that means 3I Atlas speeds up by about 13 kilometers per day compared to the day before. To put that into perspective, this force is only about 1/5 millionth of Earth's gravity, extremely tiny. Still, with ultra-precise tracking from hundreds of observatories around the world, even such a small push can be detected. Here's how scientists convert that push into a size estimate. The strength of this acceleration depends on two key factors: how much gas is being released every second, and how fast that gas is moving. The James Webb Space Telescope measured both of these values. The gas is escaping at around 1,600 kilometers per hour, while the total mass loss rate is approximately 150 kilograms per second. Using these numbers, scientists asked an important question: what size comet would make these measurements physically consistent? The math points to a diameter of about 1 kilometer, more precisely, somewhere between 800 and 1,000 meters, assuming typical comet properties. Comets are generally very low-density objects. A typical comet density is about 500 kilograms per cubic meter, roughly half the density of water. They're often described as fluffy, with lots of empty space between chunks of ice and dust. Based on this density, and the new measurements, calculations suggest that 3I Atlas has a mass of roughly 260 billion kilograms and a diameter of about 1 kilometer. According to these direct acceleration and outgassing calculations, this is what 3I Atlas appears to be. However, this is where the mystery begins. Earlier this year, from May through September, scientists were tracking 3I Atlas before it approached the Sun. Data from more than 230 observatories worldwide was used, with positional accuracy down to 0.028 arcseconds, roughly equivalent to spotting a coin from over 100 kilometers away. Despite this incredible precision, no non-gravitational acceleration was detected during that entire 5-month period. You might think they simply missed it, but that's unlikely. Their detection limit was about 300 times more sensitive than the recent measurements. If even a very small acceleration had been present, they should have detected it without any problem. This leads to an important implication. If the acceleration truly stayed below that detection threshold, then the object must be far more massive than 260 billion kilograms. A weaker acceleration means more mass is required to produce the same outgassing force. Harvard scientist Loeb previously calculated that if the acceleration was below the detection limit, 3I Atlas would need to weigh at least 33 trillion kilograms. That's 33 billion tons. At normal comet density, this would imply a diameter of at least 5 kilometers, which matches the size estimates scientists have been giving for months. So now we're left with a major contradiction. The December calculations suggest a 1-kilometer object weighing 260 billion kilograms, while the earlier tracking data demands a minimum size of 5 kilometers and a mass of at least 33 trillion kilograms. That's a 5-fold difference in size, and a 120-fold difference in mass. There are several possible explanations for this discrepancy. First, NASA has been revising the acceleration measurements ever since the initial papers were published. As scientists refine their models and account for uncertainties in telescope data, the estimated acceleration has been reduced multiple times. If the true acceleration is lower than initially assumed, the calculated diameter would increase, helping to close the gap between the 1-kilometer and 5-kilometer estimates. The second possibility is mass loss over time. The comet was likely much heavier earlier in the year, before it began shedding vast amounts of ice and dust. Between May and September, 3I Atlas was far from the Sun and relatively cold. By October, it had moved closer to perihelion, absorbing intense solar energy and losing enormous amounts of material. If the comet was significantly more massive earlier in the year, that would explain why the earlier lower bound estimates are higher. The third explanation involves asymmetric outgassing combined with rotation. If gas is being released mainly from highly active regions on one side of the comet, the resulting thrust depends entirely on the direction those jets are pointing. During May through September, the jets may have been oriented perpendicular to the orbital path, producing acceleration that wouldn't show up in position tracking along the orbit. Later, as the comet rotated and its surface heated unevenly, those jets could have shifted direction, creating measurable acceleration along its trajectory. This behavior is actually quite common in comets within our solar system. The fourth factor lies in the assumptions built into the models themselves. The calculations assume a density of about 500 kilograms per cubic meter and a certain degree of symmetry in the outgassing. Small changes to these assumptions can significantly alter the estimated diameter. If 3 iatlas is slightly denser than typical comets, or if its jets are more asymmetric than expected, the 1 kilometer estimate could increase while the 5 kilometer lower bound could decrease, potentially meeting somewhere in between. Ultimately, this is an active and evolving area of research. New observations continue to come in, models are being refined, and acceleration values are being updated as scientists work to determine which combination of factors best explains what we're seeing. This is a normal part of the scientific process. Measurements get revised, models improve, and understanding evolves over time. What makes this case especially challenging is that 3 iatlas is an interstellar object. We've never studied a comet from another star system this closely before. Many assumptions based on solar system comets may not apply perfectly here. Its chemistry, age, and thermal history could all be different. Scientists are learning in real time how to interpret data from an object that formed billions of years ago in a completely different stellar environment. Let me know your thoughts and theories about what might be happening with 3 iatlas in the comments. And if you enjoyed the video, please drop a like and some hype. God bless, and I wish you a Merry Christmas.